In this video, I would like to do another example of using Gauss's law to do a calculation of the electric field in a certain situation. The situation I want to look at this time is a spherical charge distribution. Okay, so imagine that we have a sphere like this, and it's got some, let's say, positive charge spread out throughout it. And we can kind of guess what the electric field should look like here, but let's do this directly and figure out what symmetries this has. And basically it has any rotation symmetry we want. So as long as you're rotating around the center of the sphere, it will look exactly the same as it started. And so if we imagine that there was any non-radial component to the electric field at all, something kind of like this, well, as you rotate around some axis that goes through that center, that would change. Okay, and it's not allowed to change. So that tells us that only radial components are allowed. Okay, so we already kind of knew that, but now we can see why symmetry suggests that, because otherwise we would get a contradiction if there was any non-radial component. So the electric fields point radially away from the sphere, and we want to choose a Gaussian surface where the electric field is always either parallel or perpendicular to the area vector for that surface. Now, the most natural choice, I think, is a sphere. So if I take a spherical Gaussian surface like this, where it's centered on the charged sphere, then the area vectors point directly outward, while the electric field vectors also point directly outward. Okay, so in this case, the integral of E dot dA is just going to be E times the area, because E and A are in the same direction. And that is going to be the electric field times the area of a sphere, which is 4 pi r squared. All right. Meanwhile, that is the total flux, and the total flux, according to Gauss's law, is equal to Q enclosed over epsilon naught, which in this case is just the charge of the sphere. All right, so setting those two things equal to each other, the total flux, Q sphere, over epsilon naught equals E times 4 pi r squared. We get E for the spherical distribution is equal to 1 over 4 pi epsilon naught, charge of the sphere, over r squared. Which should look familiar. That's exactly the same thing that we had from Coulomb's law. All right, so we can actually derive Coulomb's law from Gauss's law. So this is one reason why Gauss's law is considered to be the more fundamental of the two equations. Now, one kind of interesting thing to notice is I chose a sphere for the Gaussian surface, but that's not the only possible choice. So I suggest that you pause the video for a minute and try to come up with other surfaces that you could use that meet the conditions, where we have some part of the surface parallel to the electric field and some part perpendicular to the electric field. So go ahead and pause it and think about that for a moment. Okay, so one possible choice you could make is you could do, for instance, a hemisphere. So if you chose just the upper hemisphere of this, then along the flat side, you would have the electric field being along the surface. So E and A are perpendicular. And then along the curved side, E and A are parallel. That would be one choice. But you could also pick any sort of conical or any sector type shape that starts at the center and then extends outward to a spherical surface. Okay. So notice that this is basically another way of stating the shell theorem. So we know that we can treat any spherical distribution of charge as being concentrated at the center and then use Coulomb's law. And here we see that that is the case, for Gauss's law as well. So where the shell theorem took me roughly 40 minutes to demonstrate in a video, this you can do in, 4 lines again. This also justifies why we use 1 over 4 pi epsilon naught as the prefactor sometimes, rather than just using k. Epsilon naught is more of a basic physical quantity, where k is sort of derived from epsilon naught. One other thing that I want to point out is that Gauss's law, since it is considered a little more fundamental than Coulomb's law, is the first of a set of equations that we're going to talk about this quarter. Okay, so Gauss's law is the first Maxwell's equation. Okay, so Maxwell's equations are a set of 4 equations that essentially govern all of electricity and magnetism. So Maxwell didn't invent the 4 equations. He just collected them together into one compact package and made a change to one of them to make it consistent with the other 3. But if you go on to take more electricity and magnetism classes, to a large extent, it's just different ways of applying Maxwell's equations in a variety of different cases. So Gauss's law is the first, and there are 3 more that we'll get to over the course of the quarter.